We needed a compact, portable wheel balancer that could handle heavyweight wheels and tires. The Gaither GT12-1US wheel balancer handles commercial tires for heavy-duty trucks. Our 4x4 tires weigh up to 102 pounds. These wheel and tire assemblies are bulky and difficult to handle, and this portable manual tire balancer is an optimal machine for those tires. The GT12-1US is a low-maintenance and easy-to-operate wheel and tire balancer, specially designed for large truck wheels. The balancer is also well-suited for buses, passenger cars, and light trucks or commercial vehicles. This machine is economical and requires very little space. The balancer can be used in the workshop or in the field as a mobile unit. An operator can simply roll the Gaither GT12-1US mobile balancer near to the vehicle and balance the tires at that location. This step eliminates the need to move heavy wheels and tires to the machine. Once near the wheel and tire assembly, the unique design has a crank-down spindle to align the shaft with the center hole of the wheel. No more need to lift a heavy wheel and tire assembly onto the spindle. The Gaither GT12-1US is a manual alternative that provides a very accurate balance. Shipped complete with all necessary accessories, including a 5-piece cone set developed for European and USA vehicles. Included cone sizes are 44 to 74 millimeters, 72 to 131 millimeters, 122 to 174 millimeters, and 170 to 235 millimeters. There is also a 275 to 284 millimeter cone that's used for large truck wheels. The US version of this machine powers up the computer head with 110-volt AC power. The smooth, precise, heavy-duty spindle rotates easily by hand. Gaither makes balancing fast and easy. Shown in this view is a handle and cross brace that we constructed from a Wintec tire dolly handle. This enables us to easily move the GT12-1US in and out of its storage space and to the vehicle if necessary. The brace is designed in such a way that it sets back from any width tire that we would put on the machine. The machine comes with 2 drive flanges. This flange, the large flange, is for heavy-duty commercial truck tires. For our rim sizes, we will change to the smaller flange. In this case, our wheels are from the XJ Cherokee Jeep and do not require the large flange. This flange was factory installed. The flange can quickly and easily be removed from the spindle. This would be the larger flange for commercial truck tires and wheels. For our wheels on our 4x4s, we will use the smaller flange. Make certain there's no debris on the flange surface. This must mate up flush. Each of these parts are a precision fit. The flange attaches readily. A concern with any balancer is the size of the hub, the diameter, and the flange face. The mate between those two has to be square. If it's not, the tire will run out of center. And if that happens, you'll get an inaccurate balance and a false sense that the wheel itself is damaged. So before we mount the tire on the spindle, we'll take a measurement. And we have a really close match here. You can see where commercial balancers at a tire shop have been picking up the outer ring of this hub. We're going to do the same thing with this flange, which should be sufficient to keep the wheel on center, but we'll check that to make sure. For this wheel pattern of 5 on 4.5 inch, the ideal is to remove both of the adapters and use the drive plate. This is common for automotive and SUV wheels and tires. There are 3 options: 2 adapter plates and the standard drive flange. This flange will work directly against the wheel and provide a much more stable mount. The wheel will run true and will get an accurate balance. One of the most valuable components on the Gaither GT12-1US is the crank handle and ability to raise and lower the spindle and center it in the wheel hub. This was designed for large commercial truck use. No one wants to lift those large wheels and tires off the ground. This machine accommodates that heavyweight wheel and tire. Here, we lower the spindle to the height of the center line of our wheel and tire. The Cooper ST MAXX tire and wheel assembly is over 80 pounds. Of course, we could lift that onto the spindle, but that would be a lot of knocking around and heavy weight. Instead, we'll align the spindle with the wheel hub center. The highest distance of the main shaft or spindle is 620 millimeters, or 24 and 13/32 inches. The lowest distance of the main shaft is 440 millimeters, or 17 and 21/64 of an inch. Once aligned and on center, the wheel and tire can be walked into position. But before we do that, let's use the Gaither tool to remove the wheel weights and clean up the rim before we put it on the spindle. If we want an accurate balance, we need to remove all of this excess debris. Often with off-road tires, you'll actually need to pressure wash the rim. Notice that the method of balance in this case was to place the lead weights inboard and outboard of the inside of the rim. There's no provision for putting wheel weights at the outside of these rims. They will be balanced from the interior or inside rim. And in order to do that, we need a clean surface. I think we'll take the time to pressure wash these rims before we balance the wheels and tires. This wheel was balanced with the weights placed on the inside and outside of the rim. In this case, there is no provision for putting weights on the edge of the rim, so all weights are placed inside the wheel. This wheel also has the offset, with the weights toward the inside of the wheel rim and the outside. This wheel is what we call a centerline balance. There's a distinction between dynamic and static balancing, and we'll go into that when we get the machine set up. This rim also has centerline balance, with the weights placed in the center of the rim in one location. We'll remove all of the wheel weights before cleaning these rims thoroughly with a pressure washer. We like to replace commercial weights with non-lead type material. Consider that our contribution to the environment, and one of the things you can do if you're mounting and balancing your own tires. You can also be selective about whether or not to clean the rims, something that seldom gets done at a commercial tire store. Again, this wheel has the weights placed inboard and outboard at the inside of the rim. And we'll get into the dynamics of what that implies. This is the opposite side. This is not a centerline balance. always remove the adhesive before applying new weights. Make sure there's no dirt, grease, or grime on the wheels. The stubborn grease and adhesive came off with white gas and a rag. Make sure that dries completely before applying new weights, so the adhesive will adhere to the inside of the rim. Tire stores generally won't do this for you, and if they do, they would be charging an hourly rate. To protect the equipment and keep everything on center, I'd like to rotate the tire slowly while centering up the hub and cone. The wheel will now run true. We can raise the wheel and tire assembly up to a reasonable working height at this point. And this is more for convenient access to the wheel weights. We're already off the ground. The wheel and tire is now at a reasonable working height. And as you can see, it turns freely and is running true and on center. So the correct adapter in this case is no adapter at all, but to drive the wheel hub directly against the flange. Subtle imbalance is evident in that this tire on the precision spindle will actually rotate until the heavy section of the tire is pointed down. Want to confirm that? Back the tire up the other way and watch the tire rotate. The machine is in calibration, so we'll be able to move along to actually balancing this wheel and tire. Before we balance this wheel and tire, let's go over the dynamics and technological data on the Gaither GT12-1US. This machine will accommodate a rim width of 3 to 20 inches, a rim diameter of 12 inches to 30 inches, a maximum wheel diameter of 47¼ inches, and a maximum wheel weight of 330 pounds 11 ounces. When we spin the tire to balance, it only takes 15 seconds for the computer to dial in the calibration and give us data. This is a solid machine with a net weight of 357 pounds. The machine is equipped with international technology, including a microcomputer system and highly integrated stability. The machine is pre-equipped with weights optimization software. A select balance main axle is more accurate and wear resistant. You can perform both automatic dynamic balance and static balance. For alloy rims, you can balance to 3 different methods. Balance accuracy is plus or minus 10 grams each time the wheel is spun for 15 seconds. There is a self-correct and automatic diagnosis function, and this machine and fixtures meet international standards. Make certain that the stabilizer knobs are turned down. This will stabilize the chassis. Be certain that the wheel and tire are mounted properly and that the bead is seated on the tire. I always spin the tire to check for rim runout, which is really less likely with alloy wheels. They have no tolerance for bending and typically will break before they'll bend. Nevertheless, there is such a thing as factory defects in wheels. So check the runout. Look for the center line, and if necessary, either scribe a mark very carefully on the center line of the tire or use a dial indicator held slightly away from the center line to see whether the wheel is running true. Another method for doing that, of course, is the rim measurement tool, which can be very carefully brought out to the edge of the wheel and used to verify whether the rim is running out. We've got a true wheel and tire. The inside of the rim has been cleaned thoroughly, and this tire and wheel are ready for balancing. Before we begin balancing these tires, let's go over the dynamics of the tire and wheel assembly. The wheels, American Racing Bajas, are 16-inch by 8-inch. 5 on 4.5 inch wheel bolt pattern with a 4.5 inch back spacing. The offset on these wheels is 0 degrees. The tires are Cooper ST MAXX. They weigh 58 pounds apiece in their size, which is light truck LT 255/85R16. These are load range E tires with a 10-ply rating. The diameter of the tires is 32.8 inches. Tread width is 8.15 inch, and the recommended rim size is 6.5 to 8 inches. We're at an 8 inch by 16 rim. The load range capacity for these tires is 3,415 pounds. That's at full inflation. What that means in the case of mounting these on our XJ Cherokee Jeep is that these tires, if aired to full capacity, would individually support the weight of the Jeep. In this case, we run the tires at 25 psi, which gives us a load carrying capacity for the Jeep's weight. The tread depth on these tires is 18.5 32seconds of an inch, which is highly desirable for wear. We expect to get a lot of service out of these tires and are beginning our tests by making certain that the balance on the tires is right on the mark. The Cooper Discoverer ST MAXX is an optimal tire for demonstrating the effectiveness of this tire balancing machine. Let's walk through the functions and how to operate this machine. We'll start by turning on the power switch. The computer board lights up immediately. Let's zero in on the various settings and how to optimize the balance for these tires. The machine is already in calibration. We've taken the time to do that. Instructions for calibration are included with the GT12-1US. Before we make any effort to balance these tires, let's get some terminology out of the way. Static and dynamic wheel balancing are terms that come up constantly in the tire service industry. It's important to understand the difference between static and dynamic wheel balancing. Dynamic wheel balancing is generally preferred unless you're balancing very narrow wheels. Static balancing uses one set of wheel weights at the center of the wheel. This is sometimes referred to as centerline balancing. Dynamic balancing uses two sets of weights, and those weights will be placed at the outer and inner edges of the rim. On alloy wheels, like the ones we're dealing with here, there's no provision to put weights on the outside flange of the wheel. As a result, we either place the weights outboard and inboard on the inside of the rim, which would be a dynamic balance, or we attempt a static balance. It's important to note that a zero reading is not necessarily an indication that the tire is in balance, and we'll go into that further. We need to know the distinctions between static balancing and dynamic balancing. So where would static balancing work? If you had an early MB Jeep with narrow wheels, you would use static balancing. In the day, static balancing, which was done to find the heavy spot of the wheel and put the weights opposite that spot, the wheel weights were still placed opposite each other on the rim. So you had a wheel weight that was inboard and one that was outboard at the point that the static balancer found the imbalance. Motorcycle wheels are typically static balanced with the wheel weights put on a spoke on the center line of the wheel. For wide wheels and tires, like we use on our 4x4s, dynamic balancing would be preferred if it's successful. As we saw with the American Racing wheels and earlier BFG tires, both static and dynamic balancing were employed in the balance of those tires at a commercial tire shop. So what we'll do is strive for the least amount of weight in either the static or dynamic wheel balancing mode. Some say that dynamic balancing is the only kind of balancing to use on a modern wheel and tire. That the wider the wheels and tires get, the more likely dynamic balancing will work better. Dynamic balancing counteracts rotational forces both on a vertical plane and a lateral plane. Vertical or static imbalance on a wheel that's rotating will cause the wheel to spin elliptically. This is due to the imbalance weight that is wanting to fly away from its center. This causes the wheel to bounce up and down. In turn, this can create vibration and rumbling sounds within the truck or 4x4. Tires wear badly. A simpler way to look at this is that a dynamic imbalance is when you have a heavy spot that's off the center line or the midline of the tire. The off-balance spot will pull the wheel off the axis when rotating. When you're experiencing a shimmy, and this is a classic on the Jeep XJ Cherokees, called the death wobble, it can happen on any Jeep, Sometimes that's actually related to tires and the type of balance that was employed. The shimmy is the weight of the imbalance trying to pull on the steering and causing the wheel to vibrate. On a rigid axle, which 4x4s like a Jeep vehicle would have, or Dodge Ram trucks like ours, you end up with a fluttering effect. This vibration is more predominant at higher speeds. It would be a good guess to assume that that shimmy was taking place on wheels that were centerline or static balanced. Let's get going. Setup and adjustment of this machine is easy, and if you're training personnel in a shop, there's a short learning curve. First off, we turn the machine on and we see these sets of zeros, which tells us that the computer head is operating properly. The first measurement we take is the side of the rim. I like to take this to just inboard of the lip here, and our reading is 13 inches. So first off, 13 inches. Our second measurement is done with the caliper, and that's the width of the rim. We know this is an 8-inch rim, but we'll measure it anyway. Because this is an alloy rim with a flat outer face, we're actually getting a measurement of 8.5. In fact, this is an 8-inch rim width. Be cautious with alloy wheels. Often the outer flange will alter the true measurement of the rim width. Inside of the rim, 13 inches. For the width of the rim, we'll set this to 8 inches. And for the diameter of the rim, which we know is 16 inches, we'll set it to 16 inches. There are 3 modes for aluminum wheels, and these tie in with dynamic and static balancing. There is aluminum 1, which is balancing a light alloy rim by putting the weight bar on both sides. This would be the dynamic balancing method. There's ALU2 for balancing light alloy rims, where you put the weight bar on the inside or center line of the rim. Lastly, there's ALU-3, where we put the weight bar on the inside of the wheel and the outside of the wheel. In our case, we have 2 choices. We can do the centerline balance, which would be ALU2, which puts the weight bar in the inside of the rim on the center line, or ALU1, which puts the weight bar on both sides, but in our case, both sides mean the inner rim, inner edge of the inner rim, and the outer edge of the inner rim. So we'll strive first for dynamic balance and see what we come up with for a call on weight. For the dynamic method, we will first set for the commercial mode, which is for larger tires. There's a passenger car mode and there's a commercial truck mode. We'll set for the commercial truck mode because this is a larger wheel and tire. We'll also set for ALU. For an aluminum rim, in our case, these top bars tell you the position of the weights. Now we're going to set for truck. This would be passenger car. This is truck. Because we have a weighty wheel and tire assembly, we're going to use the truck setting, and we have different modes that we can set it in for aluminum alloy. This would be a setting if we had a conventional wheel and could put the weights on the inside and outside, but we don't. We have an alloy wheel. The weights will go on the inside of the rim, but what they call the outer, or toward the face, or the inner, toward the inside of the wheel. So we're going to use that mode, which is dynamic balance in this case. This is the closest we can come to dynamic balance with this style wheel. There's no ability to put weights on the outside of the rim. We're going to put our weights on the inside of the wheel toward the outside, and on the inside of the wheel toward the inside. We're going to now spin this and get an accurate read on where we stand with the balance. When spinning the wheel, we'll use the outer tread and the handle. That's sufficient speed. We'll let this run for 15 seconds, and we'll watch the computer screen for the actual weight required. in the dynamic mode for an alloy or aluminum rim. If there was any doubt about the need for a power balancer, this is the amount of spin we got from simply hand cranking for a moment. And here's our readout. This will be the inner and the outer weights. We can now apply the brake handle to stop the wheel from spinning. The outer weights will be toward the face of the wheel rim. Where it calls for 4 ounces of weight. We'll put the weight, 4 ounces, at the inner side of the inside rim. 4 ounces in this position, and at the inner edge of the inside of the rim, we'll put 3 ounces in the 12 o'clock position on the inside of the rim. You can see that there's a spacing between the two sets of weights. And years ago we would have said, well, you're counterbalancing this wheel. If this was a static balance, that would be true. As a dynamic balance, we are trying to counter rotational forces that require an inside and an outside set of weights. If we went to the center with a static balance, we would have the wheel wanting to throw those weights either inboard or outboard. And in that case, we'd end up with an applied shimmy to the tie rod ends on a beam axle Jeep. This may seem like a lot of imbalance and a lot of weight. We have a total of 7 ounces here, but considering the tire mass, and this is a load range E 10-ply tire that weighs 58 pounds on a rim that's approximately 30 pounds, we have an incredible amount of unsprung weight mass here, and 7 ounces is not a considerable amount of weight. Let's discuss wheel weights for a moment. Most tire stores use 1/4 ounce weights. And the 4 ounces that you see that need to go on the outside of the inner rim would amount to this much weight in 1/4 ounce weights. Since we're doing our own balancing at our shop, we can be more selective about the wheel weights that we buy. These are 1/2 ounce weights, and this amount of 1/2 ounce weights is the equivalent to all of that mass that you see there. So we're going to use our 1/2 ounce weights at the inner edge of the inside of the rim. So the inner weights will be placed in the 12 o'clock position at the inside edge here. So we want to hold the wheel perfectly steady at the 12 o'clock position. We will double the row. And our weights are either steel or zinc. We do not use lead weights. That's the placement for the inner weights. We now want to put 3 ounces at the outer area of the rim. Find that center point. We're going for 12 o'clock right here with 3 ounces of weight. Here's the 3 ounces at the inner edge at 12 o'clock. We're using 1/2 ounce weights again, so that makes 6 weights for a total of 3 ounces. This machine can easily switch over to gram weight if you're working with European cars or Japanese cars, and weights are given in the gram rather than ounce measurement. Let's see how close we came. Again, the dynamic balance will give us an inward and outward stability as well as the vertical stability. We're spot on now. 0, 0, 0, 0. This wheel and tire are ready for mounting. The inside of each of these wheels has been cleaned thoroughly with white gas or Coleman stove oil. And as you can see, there's no adhesive, grease, or anything else that'll prevent new weights from sticking to the wheels. Put a block of wood under this time to bring us up to the center line. Centering the wheel in this manner is called hub-centric balancing. It depends upon the wheel being true and on center. Hub has to be concentric. And if it isn't, the wheel will run out of center and balancing would be impossible. Alloy wheels are machined on center. 16-inch diameter, 8-inch width, 13-inch spacing from the machine out to the rim. The set of tires is consistent. You can verify this. You're ready to go. Truck or commercial. Method of balancing, aluminum alloy. That's stored. And this is the style of wheel balancing that we're doing. This is a dynamic balance again, with the inner weights next to the inside of the outer edge of the wheel. Both sets of weights on the inside of the rim and the inner set toward the inside of the wheel. We're now ready to balance. Need approximately 15 seconds for this to clock in. This is similar to the first tire. You can use the braking mechanism to stop the wheel and tire from spinning if you're not into using your hand. And what we have at the inner edge will go for 3 ounces. That'll be toward the inner side. That's the inner area of the rim. And the outer edge will go for 4 ounces again. This is almost identical to the other wheel. We'll use half-ounce weights again, so we don't end up with 50 weights on the tire like most tire stores do with their quarter-ounce weights. We want 4 ounces. That's 8 of these for the outer and 6 of them for the inner. That's the outer. That's 4. 2 more makes 6. That's the inner. Find the center point with all the bars lit. Weights go at 12 o'clock. These are the inner weights. We'll put them in 2 rows so that they're concentrated at the 12 o'clock point. We'll do this in one row. 6 weights isn't that long. Put one on each end. Here we will do 2 rows. We have 8 weights. These weights are not much thicker than the 1/4 ounce, so they won't interfere with the brake rotors or calipers. Let's give it a spin, and this time we won't be so zealous. It doesn't take a lot to get 15 seconds of clocking out of this. So after experiencing that weight phenomenon of balancing the tire, running it a second time and finding that it needed even more weight, we removed the weights and we're going to examine this tire under different modes of balance. So let's spin up the tire with no weights on it. The weights have been removed, all adhesive cleared. Sometimes it's necessary or worth trying a relocation of a tire on the rim if the weight is excessive. We're going to take several readouts on this. This is actually static mode. This would be weights on the center line of the inside of the rim. It's calling for no weight whatsoever. Recall that when we balanced in dynamic mode, we were placing weights 180 degrees apart at the inner and outer edges of the inside rim. So now we look at that in terms of static. This is with no weight at all, and it's showing perfect balance. That said, we can look a little bit closer and go to the fine mode, and it's showing that it needs 0.8 ounces. So we actually could put a slight amount of weight on the center line at the inside of the rim. When the machine collects information or data, it also measures in all of the other modes. So let's see what we have going on when we go to normal running mode. This would be for a wheel rim that has the capacity to put weights at the outer and inner edges of the rim flange. And it's calling for only 2 ounces of weight on the outer side in a normal running balance test. This would be if you were balancing the wheel again with clip-on weights at the inner and outer side of the rim flanges. So let's check some other modes. This would be inner and outer sides of the rim, or as shown here, inside and outside to the extremes. This is the way we balanced the first tire, and it's calling for 4 ounces and 6 ounces of weight placed on the inside inner rim and outside inner rim. 6 ounces on the outside inner rim, 4 ounces on the inside. Let's take a readout and show where those weights would be placed, because this is where we got into the problem the first time. We're calling for a weight on the inside at this point right here. Let's mark that point where it's calling for 4 ounces of weight. We mark it in the 12 o'clock position. Now let's see where it wants the 6 ounces of weight to go. When we compare those two positions, we're 180 degrees apart. So when we weight the wheel inside and outside 180 degrees apart, we're actually counterweighting the wheel. When we put wheel weights on it the last time and spun it again, it called for 6 ounces in opposite locations. So let's move to the static mode and see what it calls for in static balance. In static balance, it's showing this tire as being nearly perfect in terms of balance. We can go to the fine mode and look for the point at which it's calling for less than 1 ounce of weight. And that would be 1 ounce of weight on the center line of the tire. So in this case, we can try that. Since this is our shop and our tires, we can try 1 ounce of weight placed at 12 o'clock on the midline or center line of the rim. We'll make note of where this tire goes in position on the vehicle and exactly how it reacts. One tip-off that this may be accurate is that the tire has no tendency to fall one direction or the other and is assuming almost a near perfect balance. So let's try that. We'll put 1 ounce at 12 o'clock on the inside center of the rim. In our assortment of new wheel weights, we just happen to have 1 ounce weights, so this is not going to be a costly experiment other than our time mounting the wheel and tire on the vehicle to test for balance. Again, we are doing a static rather than dynamic balance. And this is a single 1 ounce weight instead of using 4 1/4 ounce weights like most tire stores. So this goes to the center inside of the rim. And let's spin that again. And so we're showing 0 need for weight in static mode. So let's look at that on the fine mode, and it's showing 1/10 of an ounce. That's close enough. We'll mount that on the vehicle, make note of its position, and see what kind of results we get in static mode. Again, we were going nowhere in dynamic mode, came up with worse results than before we put the weights on. So this is an instance where we'll try static mode or centerline balancing. This is our 1 ounce weight placed at the midline of the inside rim. Let's balance our third tire. Let's balance our third tire. Let's get a readout on this tire. According to the readout in running mode, we have a tire that's in balance, but let's check our other modes. It's calling for 2 ounces on the outer underside for aluminum rims. For dynamic balance, we're coming up with 4 ounces on the outside and 2 on the inner. Let's again spin it for dynamic balance. Let's apply that weight. We'll use our full 1 ounce weights, and we're putting 2 ounces on the inside. Be certain that the rim is clean. We pressure washed and cleaned these rims. On the inside at 12 o'clock, and we'll be putting 4 ounces on the outside at 12 o'clock. We'll use 3 full 1 ounce weights and 2 half ounce weights. We use 3 1 ounce weights and 2 half ounce weights. Let's spin it again and see what we get. Calling for 5 ounces at the outer end in the same location that we put the weights, and 5 ounces at the inside in the same place that we put the weights. We're resulting in a near perfect static balance. We can check that for fine balance, and we could add 1/4 of an ounce at 12 o'clock on the midline of the tire. Let's do that. We'll add 1/4 ounce, and we'll spin it again and see where our static balance comes in. Again, we're going to add 1/4 of an ounce, or 0.25 ounces, at 12 o'clock position. This is 1/4 ounce weight. Very small, incremental, but might make a difference. And we're down to 1/10 of an ounce. That's close enough, and that's our static balance mode. what we're discovering is that our findings are very similar to those on a $6,000 to $7,000 commercial tire shop balancer. Accuracy should actually be better with this machine. But that said, we're finding that 2 out of these 3 wheels required static balancing, just as they did with the earlier tires. Always protect the spindle when removing or putting a tire on. Keep it slightly elevated or bring it just to the ground without force to remove or mount the tire. So let's see what the 4th tire of the set has in store for us. Again, I'll note that these are hub-centric wheels. To be certain the wheel is on center when you tighten the clamp nut. The wheel's on center, we can raise up I can see from here that that tire's out of balance by the fact that it's trying to find a low spot. Find a reasonable work height. Do not force this handle or the gear mechanism for raising and lowering the chassis can become damaged. So let's see what we have for the 4th tire. A slight adjustment on this measurement. I've changed that to 13.5. It was a split. It doesn't seem to affect the weight. It was a difference between 13 and 13.5 inches. I'm getting a read closer to 13.5. Did a comparison on that. Didn't impact the balance, so the tires that were done at 13 are fine. 8-inch width on the rim, 16-inch diameter, commercial truck, not passenger car, but truck. These are large tires. And let's spin it. It does not take a lot of force on the spin. The balance in the spindle is such that a slight start like that will give it the 15-second runtime needed to get a data read. Slinging it any faster than that only delays the amount of time that the computer processes the information. So this lighter swing works just fine. You want about 15 seconds of runtime before you get a readout. Okay, now this time we're calling for 3 ounces on the static weight mode, 0 inner and outer on a normal side-by-side or steel rim type weight, underside of an alloy wheel, in and out. If you can put the weights on the outside, it's calling for 2 on the outside. The mode that we're using for what we're calling a dynamic balance calls for 4 ounces at the outside. So again, we have a distinction here between static, which would be on the midline or center line, of 3 ounces on the midline, versus 2 ounces on the outside if we had the ability to put weights to the outside of the rim, or in our case, with the tape-on underside weights, 4 ounces at the outside. I'm going to set this up for the dynamic balance and try the 4 ounces at the outer edge of the rim. This can be accomplished with full 1 ounce weights and minimize the number of weights used. We're going to use 4 of them. We're placing them to the outside of the wheel in the 12 o'clock position. Okay, let's see what we've got here. In dynamic mode, inner and outer weights, with the weights placed inboard and outboard at the inside of the rim, we're calling for 4 and 3 ounces. Let's compare that to static. It's straight up on static actually could call for, on fine tune, 1.3 ounces at the center line.
This dynamic balance attempt did not work out. In order to transition to a static centerline balance, the freshly installed new weights must be removed and discarded. The inner rim surface will be cleaned of all adhesive before applying new weight at the static weight position. This problem occurs because the inside of this rim has no room for adequately spacing the inner and outer weights apart. They line up too closely to the center line of the wheel and cause an inaccurate dynamic balance. This is the reason that 3 out of 4 tires in this set require static centerline balancing. The tires are not at fault, though new tires often get blamed for imbalance problems. Consumers and frustrated tire shop personnel condemn perfectly good tires when the aftermarket wheel design is at fault. OEM alloy wheels generally have clip-on weights applied at the outer edges of the rim flanges, for good reason. This spaces the weights far enough apart and at the outermost point to assure a dynamic balance. A dynamic balance can be quite accurate when the weights ride at the outer flanges of the wheel rims. Wider aftermarket rims with wide interior spacing are better candidates for tape-on weights than a narrower aftermarket alloy rim.
White gas, Coleman camp fuel, works well for removing adhesive. We keep it away from the rubber tire surface, although it's unlikely to damage that. This is strictly for removing the weight adhesive. Does a quick job. This is basically naphthalene, evaporates fast, and even if you're in a hurry, you can get this to evaporate and immediately apply wheel weights. You should wear nitrile gloves when you're doing this. Don't need to absorb any more of this stuff into your system than you probably already have. I know I can speak for myself in that regard. And try to avoid the fumes. So again, that experiment was clearly indicating that we need to use static balancing method on these tires. We had one that we were able to dynamically balance. For static balance, we're showing a need for 2 ounces. This will be on the center line of the wheel, which shows up right here. So we're going to place 2 ounces of weight at the center line of the inside of the rim. Let's check the fine adjustment on that. Actually comes up to 2.4, so we'll put 2.5 ounces in that position. Okay, so we'll use 2 single 1 ounce weights and a 1/2 ounce weight going on the center line or midline of the rim in the 12 o'clock position. Let's spin it again. Okay, we're showing a 0 readout on static balance. Let's check the fine again. Showing almost a full ounce needed. In this position. Which is actually where we had our other weights. So we'll go ahead and add 1 more ounce. See if we can get the fine measurement to zero out. It's an extension of the existing weights that we put on. Let's see if we can get this dialed in. We're showing 0. Let's see what our fine measurement is. 0.2, 1/4 ounce. Maybe. Let's see where it would take that 1/4 ounce. That's in the same location too. So what we're going to do is we're going to move the 1/2 ounce weight. We'll remove it and move it to the end of the line here. We're going to remove this 1/2 ounce weight. And we'll put, if necessary, the 1/2 ounce weight on this end. Okay, got our 0 readout, which we'd expect. Let's see where it weighs in on fine. It's calling for a 1/2 ounce. Let's see where it wants that to be. Okay, that's perfect. We'll put that 1/2 ounce at the end of this string of weights. It's calling for it in this position right here. The machine is only as accurate as the operator. Very accurate machine. Spin it again. You only need to spin this fast enough to cancel the lights. A 15-second runtime is sufficient. So zipping it up any faster than that doesn't serve any purpose, just takes longer to get a data readout. Okay, we're showing 0, but let's check our fine again. It's calling for a little bit under 1/4 ounce. Let's just see where that is. Again, these are our wheels and tires. This is our balancer, and we're in a position to, if we need to, after slight wear in of the tires, give them a chance to round a bit, we'll rebalance. Okay. Well, it's calling for 0.3. We're going to go ahead and put 1/4 ounce in that location. We're starting to creep up there a bit. It's awkward to find the midline of the tire and wheel. We're going to go inboard of our existing weights with a 1/4 ounce. Get a little bit closer to 0 here on the fine adjustment. I'm putting this again on the inside, closer to the center line of the wheel. I think that may make a difference. This is our first use of the machine. There's going to be a learning curve. We're on it. Get our 0 reading. Fine readout of 1/10 of an ounce. That's close enough for tires this size. That's phenomenal. We'll see how it runs on the road. Let the tire down. Keep it off the ground. Do not slam the wheel and tire assembly into the floor, or you will have the troubles. You don't want to damage the spindle or the computer mechanism. So the machine is fast, it's accurate, it saves us a 40-mile trip to the tire store. This works for us. I'm using a block of wood to compensate for the tire diameter. Again, this is a big tire and wheel machine. 37 1250 tires on the Ram truck will easily go to the floor and center up on the hub. Loosen slightly. Quick release. Hold this on center line. Keep the center of the hub away from the spindle. And slide it out. There's our weights. That was that last 1/4 ounce I put on there to bring it within 1/10 of an ounce of being spot on. Simply moving the weight from this side to this side did the trick. We'll put these 4 wheels and tires on the vehicle and see what kind of results we got. Nice machine. We're happy.